I'm Sumit from Innatera. I'm excited to introduce you to the spiking neural processor Pulsar. Join me as I take you into the future of brain-inspired processing for sensors. Sensors are everywhere. The world around you is filled with them. Look around you. Everything from your phone to your watch, the speaker in your room, as well as the room that you're sitting in. They're all packed with sensors, and they're all there for just one reason, to make your environment intelligent, so these devices can serve you better. Already until this year, there have been over 38 billion sensors which have shipped, and that number is going to grow to a staggering 63 billion by 2030. All of these sensors are going to produce so much data faster than we can move it into the cloud. The edge is not optional anymore, it's inevitable. Now, that's not the only problem. Today, when we try to implement applications that involve next generation AI, there's often a trade-off between accuracy, functionality, and the amount of power that's available in a lot of these devices. And practically, that means that developers have to trade off between functionality, between latency, and very often have to give up data privacy by simply taking data out of the sensor and sending it to be processed somewhere else. Another problem in all of this is that the developer ecosystem is fairly complex. There's a multitude of accelerators that application developers have to deal with in order to develop performance solutions. And all of this simply complicates the development process and increases time to market. And that's where we at Innatera set out to build the impossible, to bring the brain's efficient processing to sensors everywhere. We put together a fantastic team that came from some of the world's most well-known startups and companies, a team that had been involved in developing some of the best microprocessors that the world has seen and some leading analog mixed signal technologies that you find in products around you today. We built out a really strong board of directors that included people like Alberto Sangiovanni-Vincentelli, the legendary founder of Cadence and Synopsys. And around these people, we built a team of close to 100 talented engineers working across 15 different countries to change the way we process sensor data in these battery-powered devices. In order to do this, we tapped in on over a decade of research that was carried out at the Delft University of Technology from the early 2000s. We put together all of this research into neuromorphic computing and energy-efficient processing, and we brought it together to form Innatera in 2018. Over 6 years of R&D that followed, we intensively de-risked what is a fundamentally new approach to sensor data processing, leveraging the mechanisms that we find in the human brain. And today, I'm very happy to tell you that we've taken these technologies into mass production in the form of a microcontroller. And I'm excited to introduce you to the spiking neural processor Pulsar, the world's first neuromorphic microcontroller which brings truly brain-like intelligence to sensors. Pulsar is the only microcontroller that a sensor needs. It enables high-performance AI capabilities to do always-on processing of sensor data directly next to the sensor. It is phenomenally energy efficient. It cuts energy use by over 500x compared to traditional AI approaches and traditional computing approaches used in the industry today. And that means devices that will simply last so much longer without you having to recharge them. At the same time, these processors enable you to process sensor data about 100 times faster than anything which you find in the industry today, enabling truly on-device AI with unprecedented capabilities that the industry has so far not seen. And we pack all of this into a really tiny package of about 2.8 by 2.5 millimeters. Truly big impact in a small form factor. The secret to all of this winning combination, is neuromorphic or brain-like. The Pulsar combines a heterogeneous, a radically new compute architecture that is built to mimic the brain, and that is complemented by brain-inspired neural networks, which are compact, sparse, and extremely energy efficient. Let me show you this in action. Here's a great video from the Howard Hughes Medical Institute. It shows the neuronal responses of a zebrafish, which has been modified to express them in light. What's very clear to see in this video is that as the neurons in the zebrafish brain fire, they fire in groups. As they are stimulated by sensory stimuli, discrete groups of neurons fire together, seemingly recognizing what's happening in the world around them. And you can imagine this in a very simple way. Every time you hear someone speaking, each word that comes out of their mouth, there's a unique cluster of neurons in your brain that recognize it. And that's the secret to how the brain recognizes and processes information so efficiently and so quickly. The way we do that in the electronics world is by using something called a spiking neural network. This is a neural network which very closely mimics the firing mechanisms that you see in the brain. And the way it works is really simple. As stimuli come in from sensors, the stimuli are converted into a set of very simple voltage spikes. And the interesting bit here is that the critical information from the input sensor data is encoded into exactly when these different spikes occur in time. The spikes are then injected into a trained neural network model that is designed to manipulate the timing relationship between all of these spikes. And by doing that, the network is able to detect patterns inside of the input data. It's able to extract features that allow you to do more with that sensor data. And it also allows you to condition that sensor data to remove artifacts like noise or increase or amplify features that you're interested in. These networks inherently have the ability to recognize time, and that makes them so powerful. In fact, spiking neural networks with the same application at the same level of accuracy can be over 100 times smaller than an equivalent non-spiking neural network that you currently use in the industry today. And that's what we built Pulsar for. Pulsar is the world's first neuromorphic microcontroller, and at its heart is an engine that is designed to run spiking neural networks quickly and efficiently. Here's a picture of what Pulsar looks like. It's a combination of 3 different compute fabrics. On the top right, you see an accelerator for spiking neural networks. This is a large segmented accelerator that runs spiking neural networks in a massively parallel fashion atop an array of analog mixed signal processing elements. Each of these elements mimics the same behavior that you find in biological neurons. Essentially, every time operations within the neural network are fired atop this accelerator, they execute with a minuscule latency with a radically small amount of energy. And this makes it possible to carry out inference on data in real time using very little power and to have it done very quickly. This accelerator is complemented by a traditional non-spiking CNN accelerator. And this simply provides application developers with a complementary set of tools that they can pick and choose from when they're developing applications. So you get to deploy the best approach for the problem that you've got at hand. And finally, Pulsar integrates a RISC-V CPU subsystem for all of the housekeeping and system management that happens around neural networks. Altogether, Pulsar packs into a single tiny chip a powerful set of compute intrinsics and compute fabrics that allow you to do end-to-end processing of sensor data within a very, very small power envelope. And the results speak for themselves. Spiking neural networks running on Pulsar outperform traditional approaches by leaps and bounds. Here's a picture which shows you the impact across a few well-known use cases in the industry. And remember, these are not simple applications. These are complex applications which today find their place in products. In something like audio scene classification, we outperform traditional approaches by a factor of 100x in terms of energy consumption. And those same benefits even carry over into more complex applications like radar gesture recognition, where we outperform our closest competitors by a factor of 42 in terms of our inference power dissipation. To add to this, we reduce model sizes compared to traditional approaches by several orders of magnitude, simply reducing the amount of memory which is required in these devices. And we do all of this while sustaining extremely high accuracies so that you no longer have to trade off between accuracy, functionality, and power in your devices. And Pulsar is already having an impact on a wide range of use cases in the industry. We've got some stellar applications that show exactly what we can do with Pulsar in improving audio quality in something like headphones that need to adapt themselves as you move from one scene to another. We've shown phenomenal success in human presence detection using sensors like the 60 gigahertz radar as well as far infrared. And this is going to be supremely important in devices like security cameras and smoke detectors that are designed to make our living spaces more intelligent and which can serve us better. We also see Pulsar going into applications where they're monitoring machine health, giving you an early warning when a machine is about to fail, and doing that inside of a monitoring patch that is designed to run for years without the battery ever needing to be changed. And close to my heart, in applications that involve cardiac monitoring, allowing true smart diagnostics to be brought to every person around the world in the form factor of a device that simply sits on your hand the entire day. And there are so many more. We are rolling out these applications across different markets. We are extending our capabilities with Pulsar into more use cases within the audio space, into the smart building space, as well as in industrial IoT and wearables. The future is exciting, and Pulsar is enabling all of that. Complementing all of the silicon innovation which you find inside of Pulsar is the Talamo software development kit, which makes it seamless and easy to deploy models onto our silicon. Talamo is a sophisticated set of tools that makes it simple to go from model development to deployment on top of our chips. Talamo is integrated into a PyTorch-based front end, and this provides developers with a very familiar environment that they're used to today to build models. And we've extended into this environment capabilities to build spiking neural networks, basically taking the complexity out of all of this process. So now you build and train your spiking neural networks directly inside of that familiar PyTorch environment. And once you've got a model that you're ready to deploy onto hardware, you exercise our compiler, which maps in a turnkey fashion that model onto our chip without the application developer having to understand any of the intricacies of Pulsar's architecture. Talamo is designed to make the model development and the application development process simple, turnkey, fast, and standard. Our objective is to lower the entry barrier for embedded developers that want to deploy applications onto the next generation of intelligence for sensors. Pulsar and Talamo together solve the edge trilemma. Pulsar brings to the table unprecedented power and performance capabilities. It takes the trade-off out of the application development experience. Application developers now no longer need to choose between low power, fast application performance, or complex functionalities next to the sensor. They can have all of them at the same time. Pulsar also eliminates the latency and privacy concerns that come with traditional AI. You no longer have to move raw data from the sensor up into the cloud to be processed by a performant algorithm. You can now do that on device. And that simply means applications which are responsive and snappy. And you now eliminate that problem of taking user private data and sending it into a device which is outside of their control. And most importantly, Talamo eliminates the need for you to have a neuromorphic PhD to build applications to run on neuromorphic solutions. It simplifies the process for application developers and makes neuromorphic intelligence accessible to everyone. And on that note, I'm happy to announce our developer program, which will provide the latest Pulsar evaluation kits and the Talamo SDK to our growing ecosystem of researchers, developers, and industry partners. This will enable the development of future applications based on our cutting-edge neuromorphic technology. A new era of edge AI starts now with Pulsar. Join us and let's make the world intelligent.